Hey guys, this is Mrs. Harbin, and this is Pre-Cal Chapter 2. We have been looking at linear equations, quadratic functions, and now we're going to look at 2.4 polynomial functions. This should be a review of a lot of what you did last year in Algebra 2, so I'm not thinking that this is new information. I am going to go through it rather quickly. Our biblical correlation comes from 2 Chronicles 26:6, which says that Uzziah built towers in Jerusalem at the corner gate, at the valley gate, and at the angle of the wall, and he fortified them. We know that mathematics is useful beyond just the four walls of this classroom, that God has created math and precision and measurement for us to be able to go out and make a difference in the world. And we see that here in 2 Chronicles. And we know that we need to be precise in how we use math more than just doing well on the test. The lesson objective for today is that you, the student, will identify, find the degree, evaluate, perform operations, and find zeros of polynomials. And yes, I know there was a typo on that. I will have to fix that when this video is over. In a polynomial containing a single variable, the highest power of the variable is the degree of the polynomial. So in a linear polynomial, where our x has an exponent of 1, then that is the degree of the whole polynomial. In a quadratic formula, quadratic polynomial, our x has an exponent of 2, therefore our degree is 2. Cubic, the degree is 3. Quartic, the degree is 4. And in quintic, the degree is 5. When you have multiple x terms, to determine the degree of the whole polynomial, you look only at the term that has the highest exponent, in this case, the 5. Now, this is a really long kind of formal definition of a polynomial. But basically what this is saying is that in a polynomial, you're going to write your terms in descending order. So let's give some numbers here. Let's say that this exponent n is actually a 5. The next term that we would write would be x to the n minus 1, which is 4. And then x to the n minus 2, which is our cubed term, all the way down to our constant term, which has no variable. No variable. So we write our polynomial in descending order. That's a long formal definition that essentially that's what that's saying. Okay. Also, our constants here, our coefficients, must be real numbers, and n must be a whole number. We can't have any fractional exponents there. That last term without a variable is called our constant term. A constant polynomial has no variable terms and a degree of 0. So an example of a constant polynomial would be y equals 4. It is a polynomial, it has no variable, and it has a degree of 0. The zero polynomial, y equals 0, has no degree, whereas this has a degree of 0, this has no degree. Let's describe this polynomial. The first thing let's do is let's put it in descending order. Put it in the correct order. Remember that the operation signs immediately in front of the terms. Stay with them when we arrange it. So this should end up being a positive 8x to the 4th minus 7x squared plus 5x minus 9. What's the degree of this polynomial? Hopefully you knew it was 4. What about the leading coefficient? Yep, it's 8. And our constant term in this case is negative 9. Keep looking at that polynomial and see if you can identify the coefficients of the x cubed, x squared, and x terms. You should see there's not an x cubed term, so the leading coefficient must be 0. Because 0 times x cubed would be 0. We won't see it. And our x squared and x terms coefficients are negative 7 and 5. A polynomial function is a function having a polynomial for its rule, such as p of x equals, and there's that definition of a polynomial again, where our coefficients, a to the sub n, a sub n minus 1, all the way down to our constant term, they're all real numbers. And the leading coefficient is not 0, and n is a non-negative integer. So we can't have ax to the negative 5, for example. We cannot have negative integers as exponents and still be a polynomial function. So let's take a look at these three, see if you can tell me if they are polynomial functions and what their degrees are. Yes, this is a polynomial, and it has a degree of 2. It meets all the rules of a polynomial function. What about this one? This is a constant polynomial, so yes, it is a polynomial, and it has a degree of 0. Hopefully you noticed that negative exponent there, and you knew that it was not a polynomial. You cannot have a polynomial with a negative exponent. When we're evaluating polynomials, it's just like our other equations that we are evaluating. We take the given value, in this case find p of -1, and we plug it in. So we're going to plug -1 in everywhere there was an x. Remember that when you're substituting in numbers to use parentheses, this will help you to honor those operation signs, not get your negative signs confused, and will make sure that you're using powers correctly. So use those parentheses when you sub. When we simplify this, we find out that p of -1 equals 16. Polynomials can be added, subtracted, multiplied, and divided with other polynomials. If you're given two polynomials here, like p of x and q of x, you can subtract them. So let's find p of x minus q of x. Again, we're going to use parentheses here around our polynomials so that we can honor this operation sign. This will also help us remember that we need to distribute that negative sign. If we had not put those parentheses there, we might have forgotten to distribute that negative. We'll then combine like terms, and we'll know that our polynomial is simplified when there are no more parentheses and all like terms have been combined. And we can also divide polynomials. So we're going to find q of x divided by p of x. And hopefully you remember how to divide polynomials here using long division. I'm not going to talk you through each of these steps. If you need a reminder on long division, we can take a look at that in class. When we divide those polynomials, we get 2x plus 5 with a remainder of -7. Finding all the zeros of a polynomial function may require factoring methods and the quadratic formula. Remember, finding the zeros means that we're finding the values of the variable that make the polynomial 0. It's also how we find where they cross the x-axis, because those are the points where y equals 0. Find any zeros of p of x for this particular polynomial. Step 1, we're going to set the whole thing to 0, and we're going to try to factor it. This cannot be factored, so we do need to use the quadratic formula. And by plugging in our values into the quadratic formula, we get that the 0 of this particular function is -6 plus or minus square root of -60 over 2, but we can simplify this a little bit farther. We know that -60 is an imaginary number, so let's go ahead and simplify that to 2 square root of 15i, which can be simplified even further to -3 plus or minus 15i. What about finding the zeros of this equation? Well, the first thing we want to do is factor it. And to factor it, we're going to take our leading coefficient, multiply it by our constant term, and that gives us 22. And our middle term here, squared term, is going to go right here, that coefficient. And we need to find two numbers that when multiplied will equal 22, but when added together will equal -13. And I know that -11 and -2 meet those requirements. So I'm going to break this middle term apart into -11x squared and -2x squared. When I've done that, I can factor by grouping. Again, this should be a review. If you need help with this, we can go back over it in the next class. Once I've factored by grouping, I'll take each of those factors and set them to 0. And I find out that x is plus or minus root 22 over 2, or x equals plus or minus 1. Today we identified, found the degree, evaluated, performed operations, and found zeros of polynomial functions. If you guys have any questions, we will go over this next class.